I will now hand over to Patrick, who has an academic position at Columbia University as a professor and in Johnson & Johnson, and is the founder and world expert on all things OHDSI and common data models. Patrick,
Great.
Thank you.
Thank you, Adrian. I want to thank the ARDC for inviting me to come and get to hang out with you guys. Just so I know who I'm dealing with, everybody is in the room. Are most of you guys staying tomorrow too? Raise your hand. Who's like excited to geek out on data for the next 2 days? Most people's hands up. Okay. All right. And for those that are online, hopefully you can hear me well enough. I can't see the chat. So Long, can I ask you that if you see someone chatting, yell at me and I'll answer the question. I just can't see it from here. So Nicole, level set for me. I just want to make sure that I'm doing the right thing. Today, I'm going to give you all a rundown of OHDSI high level. This is going to presume that nobody knows anything today to try to get you up to a spot where tomorrow we're going to dive deep into how you actually ETL a data set into the OMOP common data model and how you do some basic like phenotyping. But today is going to be basically just like giving you the big picture of how all the pieces fit together. That's what we want to do. Yep. And we have an hour and a 2 hours. 2 hours. Okay.
So we've gone.
Okay. So I've got a lecture that if you just let me be long-winded, I'd probably finish in like about an hour or so, but I would prefer not to just yell at you the whole time. So please do stop me, ask questions, challenge me, complain. If you don't understand something, please raise your hand, because the goal is get everybody to the common level of like what we're trying to actually do. And for those that are on the line, please do. Fair enough, Paul. Fair enough, Paul.
Paul also has an American accent for context.
Please do let's try to have this be as much of a conversation as possible. I purposely didn't prepare like 2 hours of lecture because I'd like for us to have open conversations, which can bleed into like what we're going to do tomorrow and throughout the entire project over the next 3 years as we're trying to collaborate together. So why don't we get started? So I'll also just in disclosure, as Adrian mentioned, so I'm a professor at Columbia University in New York. I also work at Johnson & Johnson. I'm the head of our observational health data analytics group. I'm going to be talking really in my capacity of leading the OHDSI community in what we're doing at large, but where possible, I'll try to bring in experiences from what we do at Columbia and what we are doing at J&J as well. And I'm happy to answer questions about any of that, how that fits, particularly as you all are thinking about what this means for your own institution and how you can be contributing to your organization's goals, but also like what's in it for you and what's in it for your organization. So let's get started. So what we're going to be talking about is the journey from going from data to evidence. And I think all of you are here that geek out on data recognize and appreciate that this is a hard journey that we all frequently try to undertake. And it's actually the motivation and the recognition that it's really hard to go from some sort of data that's originally captured during routine clinical care to some sort of piece of reliable evidence that we want somebody to take action on. Like that process is hard. And because it's hard, it takes us a long time. Because it's hard, we don't necessarily always do it consistently. Because it's hard, we don't always do it as much as we would like to do. And part of the challenge with this is that there are lots of different types of data that we want to engage with. There's lots of different types of evidence that we want to be able to produce. And yet each one of those basically involves us trying to go and do some sort of data munging from the data to get to the point where we can produce some evidence. And a lot of what we've been trying to do is just to figure out like, how can we make this process a little bit less painful, a little bit higher quality, and ultimately get us to the point where we can generate evidence in a more reliable fashion. So when I'm going to talk about patient-level data for the purposes of just orienting my presentation here, I'm going to be talking about observational health data. This is data captured during routine clinical care. This could be an array of different data. And as I've begun to learn a little bit about the Australian healthcare system, I see a lot of these differences in the respective organizations that are represented. But there are different types of observational health data we can think about. We can think about differences on multiple dimensions. So There may be differences in populations. I know that you have, like, for example, you have children's hospitals, especially hospitals, and you've got aging care as one of your groups. There can be population differences in terms of socioeconomic disparities, whether that in your case even just being something as simple as the private versus the public hospital systems. Care setting can be a difference in terms of data capture, whether that be hospital care, same-day care, admissions and discharges, or outpatient care, whether that be primary GP or specialty care in or out of the hospital. The data capture processes can be different. There are administrative claims. I understand that there's, and I'll probably butcher my understanding of the Australian health system, but what I've come to understand is part of the reimbursement process is facilitated by standardizing some data, and that takes the form of specific information extracted from electronic health records. But there are also clinical specialty registries, either disease specific or other areas. Each represent different manners in which data are either captured or manipulated. And then, of course, the health system itself can have specific dynamics. So very frequently when we actually talk about the observational health data, and particularly a lot of people use the buzzword about real world data, there is no one kind of real world data. There's lots of different types of real world data that we're all trying to interface with. On the other end, there's lots of different types of evidence that we would like to be able to generate. And just as a type of classification of what we could learn from data, I like to classify things in really three primary buckets. There are questions about clinical characterization, where we're performing descriptive statistics about the data to summarize what have we observed in a given population. And this has a lot of specific applications. It can support clinical research by just helping us identify which patients are eligible for a clinical trial, for example. It can support us in evaluating treatment utilizations, understand like how many people are taking a particular drug, or how many people have undergone a particular medical intervention, and whether or not those trends have changed over time. We do a lot of descriptive summaries about disease natural history to understand who are the patients who develop a disease and what happens to them following the disease. And a lot of our efforts in hospital systems and even our operational activities can be couched in quality improvement efforts. You know, just understanding what proportion of people receive the kind of expected care that one would anticipate. All of these can kind of fall under the umbrella of clinical characterization, where we're just talking about descriptive statistics that we can generate from real world data. Here, it's very often the case that the integrity of our descriptive statistics lie in the fact that we need to be able to define our populations in an appropriate way, and understanding the extent to which the data is sufficiently high quality so that when we're counting up things, that we're counting them up correctly. A second dimension that we can classify things is population level effect estimation, or causal inference. So for example, we may want to study the safety of a particular medical intervention. You know, does a drug cause a side effect? We may want to study the comparative effectiveness of medical interventions. Is some drug therapy better or worse than some surgical intervention for any given disease? Here, the questions of causal inference require us to apply advanced statistical methods for us to be able to produce unbiased estimates of effects. So we actually are trying to explicitly answer causal questions of the ilk that we would very commonly think we might need to conduct randomized clinical trials to answer. But we want to be able to try to produce valid insights through retrospective analysis of this real world data. So now we have to not only worry about issues of data quality and completeness of capture of information, but now we have to actually worry about the bias in our statistical analysis as well. And a third area that a lot of people are excited about, actually I'll ask show of hands, how many people are feeling like you're part of the AI hype cycle right now? Who's all in on machine learning right now? Not too many, only a couple? A few, okay. Yeah, I was assuming you were gonna raise your hand, Bob. So when we talk about patient level prediction, we can explicitly think about how could you use data such that you could take an individual and predict the likelihood that they're going to experience some future event, given what you know about them in the past. And this has tremendous applications as it relates to precision medicine or disease interception. You know, can I predict which patient's going to go on to experience some untoward outcome, with the idea that if I knew which patients were at higher risk, maybe I could come up with some sort of intervention to manage that. This requires application of machine learning algorithms on our observational data. Now it becomes a question both of data quality. You don't have to do causal inference. You're just doing non-causal inference in terms of machine learning, but we actually need to know to what extent do these prediction models actually correctly discriminate between those that really go on to have an outcome versus those that don't. And so for all of these use cases, we need to develop analytical tools to generate this type of evidence. And we need to have ways to think about how do we prove that that evidence that we generate is reliable. And each of these different classes have different ways for us to think about evidence quality. Now, I am a large advocate for the use of real-world data and generating real-world evidence, but I also recognize that the space of real-world evidence that we exist in today is quite problematic. And I'm going to make an argument that to assert that the reason why observational research isn't trusted is because the process that we use to generate real-world evidence isn't a very trustworthy process. And so I'm going to lay out a process that at least I see happening all around the world. I don't know if it's what you all do, but I'm going to guess that for some of you, this will kind of resonate with how you might think about doing your research. So typically, most research or operational activities start with somebody specifying some research question or some idea that they want to answer to the piece of evidence that they want to produce. That usually should take the form of somebody writing some sort of protocol. That's a specification document that describes what you're trying to do and why. In an ideal world, that protocol would be reviewed by somebody else so that you make sure that it's a valid question and that you have a valid approach. That may or may not happen in all circumstances. But ideally, you'd have a protocol written as some sort of a document that provides the guide to what you do. And then we go through a series of steps of curating data, identifying populations, like, for example, the people who have exposure to a medical intervention or experience some sort of outcome. We then apply some statistical analysis to this analytic ready data set that we've created. We generate some results, and then we seek forth to go through and disseminate that evidence. Me, as an academic researcher, that's very commonly like through peer review publications. And so does this resonate? Does this kind of feel like how you guys do a lot of your work? I'm seeing some head nods. For those of you that go through this process, you've probably experienced the same frustration that I do, which is at the very end, you go to disseminate your evidence by, for example, writing a paper and submit it to a journal. And that's when you get the dreaded reviewer number 2, who basically asks the question, is the evidence reliable? And here's actually where the whole system breaks down, because at this point, a reviewer has not only a description of what you did, but has the answer to the question that you sought. And so they're already biased. If they like the answer, they might be more lenient. And if they dislike the answer, they may be more stringent in terms of what they review. But ultimately, what the peer reviewer is supposed to do is say, do I trust this piece of scholarship that was just generated? And there's tons of reasons why they shouldn't trust it and very little proof that they should. So some of the reasons why they may be concerned might be methodologic issues. Like, for example, they could challenge, did you apply the right statistical methods that actually yield unbiased estimates? If you're creating phenotypes to define populations, are they subject to measurement error? What is the sensitivity and the specificity of capture of disease? From the data perspective, there's always questions of data quality and completeness and conformance that people can question whether or not there's integrity to that. And really, these methodologic concerns get at the question of, given these limitations, can we actually believe that the answer that you produced is true? There's a second set of problems which are really sinister, which are very basic, mundane technical concerns. Like, how do I actually know that your programming code is correct? As a peer reviewer, I see some article and I read this very elaborate approach they take, but I don't have access to the code. I don't have access to the data. So I just got to hope that maybe somewhere somebody possibly QC'd and ran some sort of unit test on a code. That said, I know that my PhD students at Columbia, they write a lot of code. I don't QC it. I don't actually know whether it works. I sure as heck know that my PhD, nobody looked at my code. It's almost certainly all buggy as all get out, and wouldn't trust it for anybody. But our current modality of generating evidence is somebody writes some code and then we kind of hope that the code kind of works and generates results. That also goes back to the logic. If I said that I've defined a population, did I actually implement what I said in the exact way that I said it? And what we're going to talk about a lot tomorrow is, if data has to be manipulated in some sort of format, converted from one format to another, how do you actually verify that that data transformation process happened without error? And so these technical concerns really get at the heart of reproducibility. If I read a paper, how confident am I that if I were given access to the same data and perform the same operations, I could actually get the same answer? And as a peer reviewer reading a paper, almost always I look at this and say, there is almost no chance that I could reproduce this result, both because I don't have access to all the necessary artifacts, but also they are not necessarily specified sufficiently, and there may also be these other concerns that are going on. And my reading of 99% of the published literature, including 99% of my own published papers, is that I'm not sure how the outside environment should really be able to trust this unless we come up with a new paradigm and a new system for engaging and building trust. So within the OHDSI open science community, we've been thinking a lot about this problem of how do we create a structured approach to generating evidence that can actually help us with building trust in science. One thing that we've thought about is like, what constitutes reliable evidence? And we've identified a series of desired attributes that we believe are kind of like basic features of what constitutes good science that we would lay out. And for the most part, and I'll ask you guys as a assessment to see whether or not you agree that these are necessary elements. And so I'll go through them here. So one is that basic science should be repeatable. That is, you as the researcher, if you have access to the exact same data and you run your exact same analysis, you better be able to produce the exact same result. Show of hands for the last analysis that you all performed. How many of you are 100% confident that your result is repeatable? Show of hands. I got 1/2 of a hand. Oh, I got a quarter. I got 3/4 of a hand in the whole room. So everybody else is not feeling so good about repeatable analysis. Okay. I don't know about you guys, but like in my first elementary, physics class, whatever, we did like ticker tape experiments. And like the whole point was like, you're supposed to run the experiment multiple times and show that you get the same result over and over again. And like that was born into me, like, this is what science is about. And yet, indeed, I can tell you, I didn't raise my hand when I asked you that question because some of the analyses that I've published in the past definitely weren't repeatable. And usually it's because we don't have a system to generate evidence. Instead, we have that meandering journey that I drew with that squiggly line where like I had data and I did something and then I learned from it and I did something else and I did something else. And if I had to trace back my steps, it's just really hard. The work that we all do to work with healthcare data to generate evidence is difficult, and it makes it hard to do it in a systematic, structured way. Now, repeatability is just the very first one. The second one that I'll assert is reproducibility. You'd like to be able to believe that not just that you could repeat your work, but that if you had sufficient transparency and description of something, that you should be able to give the exact same data set with the exact same analysis to somebody else, and they should be able to run it and generate the exact same answer. This requires a level of transparency that most of the time we do not see in observational healthcare research, because this level of transparency means full specification of every step that's been performed, not just described in human language words, but also codified in code that should be able to be executable start to finish. How many of you have done something that you are confident is reproducible by somebody else? Show of hands. I got 3 half hands. Okay. All right. So we got some people that think some of their stuff is reproducible. Okay. So these are kind of basic requirements. The next one would be replicability. So very often what we're interested in is not just that you can actually verify that you performed an operation, but that if you were to perform a similar analysis on a similar data set, you'd get a similar result. And very oftentimes when we hear about the replication crisis in science, it's usually because there's a lot of excitement for the person who publishes the first analysis that gets a p less than 0.05, and there's a lot of less excitement about the person who comes around a second time to verify if that effect was actually real or if they don't confirm the finding. But replicability in our context usually means you need to perform an analysis on some data set and then have access to some other data set to perform an analysis. Now, many of us as researchers, getting access to data is the hardest part. You're lucky if you work for one institution and have access to one database. To have access to another database means like now you've got to figure out how to work with somebody else who has another data set. So already the complexity of doing research that can be replicable in our healthcare database is extremely hard. The fourth one is generalizability. So it's not just that you would like to be able to show that you can get the similar result in a similar population, but actually ideally you'd like to be able to know that even if you were to apply an analysis on a different population, you'd get similar results. being here in Australia, one of the things that we've been talking about is where does evidence come from that impacts the lives of Australians? As it relates to drugs, very commonly, we're using information that's been learned from studies in Europe. And then there's a real question of like, do we actually believe that what's happened in Europe generalizes to Australia? Or similarly, if we observe something in Australia, to what extent do we believe that that's actually going to be applicable to the rest of the world? But in an ideal world, generalizability would be useful. The fifth category here, robustness, is about trying to verify that the analysis result that you generate isn't just sensitive to the whims of whatever statistical analysis you performed. You know, there are lots of design choices that researchers get to make. If you're an epidemiologist, you may be thinking about different study designs. If you're a statistician, you may be thinking about different models. But ultimately, if you've got a robust finding, it shouldn't matter what statistical model or what study design you've selected. You should be able to produce a consistent answer. And ultimately, most of what we're doing is generating aggregate summary statistics, whether it be descriptive statistics like the incidence of an outcome, whether it be a causal inference like a hazard ratio or a relative risk estimate about a causal effect, whether it be a machine learning algorithm that's actually going to produce some predicted probability. Whenever we produce a statistical artifact, we'd like to know that we can actually trust that that number we produce is actually correct and it means what it's supposed to mean. These are all basic requirements of what we would constitute reliable evidence. And my assertion is that for the vast majority of research we do, we fall short on most, if not all, of these attributes. So those people that are out there that are saying like real world evidence shouldn't be trusted, I'm sympathetic to the position that they take, because most of the evidence that's been published probably shouldn't be trusted. But rather than having an argument about whether or not everything needs to be randomized clinical trials or whether real world evidence can be useful, what I think becomes a more important conversation is how do we change the way we do research to generate evidence that actually can satisfy these criteria so that all of us can trust it and so that the evidence that we generate can actually become actionable to whatever health decision that we're trying to inform. So with that, what I'm going to talk about is the OHDSI community, this open science community that we are running, which is really aimed towards trying to enable reliable evidence generation. Our mission is to improve health by empowering a community to collaboratively generate the evidence that promotes better health decisions and better care. And explicitly, as an open science community, our goal is to bring people together from all different stakeholder groups, whether you're industry or academia or government, from all around the world, from all different disciplinary perspectives, anybody who shares an interest in a belief that healthcare data that's captured about an individual should be able to be responsibly analyzed to generate evidence that can improve healthcare. If you have a shared interest in that, we want to be a place where we can advance the science together to make that possible. A lot of what I'm going to showcase is part of our OHDSI annual report, and I'm just providing this this URL, and all the slides that I'm sharing will, I don't know how we'll share them, but they're going to be available to all of you, so you're welcome just to see this. But this is a book that we publish every year, just kind of a summarize of the current state of our community, and I'm going to highlight some of the components of that. So OHDSI is an international community. We've actually grown quite large. We now have over 4,700 collaborators in 88 countries. What does it mean to be an OHDSI collaborator? It means you went to the website ohdsi.org and you just signed up by saying, hey, I'd like to be a collaborator. It is totally free to be an OHDSI collaborator. Hopefully some of you already have signed up, which just means you just sign up and put your email in. But it provides you the opportunity to collaborate with all of these other researchers around the world. It is very much deliberately and purposely a global community where we try to figure out ways to foster collaboration around the world, but we also have various regional focus and activities. And like, for example, Nicole leads the OHDSI Australia chapter to support activities that are happening within the country, and is also part of the leadership of the OHDSI Asia Pacific region to try to facilitate things in this region, as well as participating in global efforts. It is a lot of people with a lot of shared interest. In the most exciting and rewarding thing for me is to see how many people from around the world actually also geek out on things like, let's play with healthcare data to generate insights and figure out better ways to do science. The way we work as a community is anybody, any individual who has an interest in some topic can basically raise their hand and say, hey, I'd like to create a work group on some topic of interest. If any of you in this room have an interest in saying, I'd like to work on some particular problem, you are welcome to start a work group in the OHDSI community. Basically, as long as somebody else shares an interest in the problem that you've got a work group, and you can actually start working on whatever problems. We have a wide range of different activities. These are all the smiling faces of all the leaders in our community that are leading various groups. And I'll highlight the types of activities that we do just to give you a motivation for this. So we've got folks that are really interested in data standards. So we're going to talk a lot about the OMOP Common Data Model, the OHDSI Standardized Vocabulary, tools for ETLing data, data quality conventions, and we've got work groups in those various areas. And if like you're total data wonk and you want to, there's lots of people that like to geek out on that too. We've got work groups that are focused on methodologic research. So people that are trying to figure out best practices for doing machine learning and patient level prediction or causal inference. Groups that are trying to figure out best practices for phenotyping to define and evaluate algorithms for finding patients in data sets. We've got work groups in open source development. So if anybody's loves to hack code to write either like front-end web-based interfaces or back-end R packages or Python or whatever might be your favorite language, we've got work packages that are creating tools for the community to enable their analyses. And then we've got various work groups that are specifically focused in clinical areas, whether it be clinical subspecialties like oncology and psychiatry or rare diseases or perinatal health. Basically, folks that are motivated by a common interest in a particular clinical area, they get together and they figure out how are we going to work together to advance the science of real-world evidence in this space. All of the work groups are freely available. So like when you sign up, if you haven't yet, you join the OHDSI community, first thing you're going to do is just get a free account to go join any of our OHDSI activities. And then the second thing you'll be asked is, which work groups would you like to join? They are totally free. You can just click on whichever ones you'd like to go attend. You just join a meeting, meet some friends, figure out if you want to collaborate, and jump around until you find your home in the community. We also have regional nodes, regional chapters and national nodes. So I mentioned like Nicole leading our Australia chapter, but we also have regional and national chapters and a very active leadership in lots of different geographies, which really provide opportunities to bring people together in the same geography that are like sharing the same pain point. So here in Australia, there's a lot of common problems that are specific for Australia that you guys can work together on. And the OHDSI Australia chapter is a good place for you to have a forum to collaborate together. One thing we're going to spend a lot more time on, particularly tomorrow, is the OMOP Common Data Model. As Adrian mentioned, the OHDSI community is the steward of this OMOP Common Data Model. How many of you have already worked with the OMOP Common Data Model? Raise your hand. 5 of you. Okay. So for the 5 of you who've already worked with it, if it's been frustrating, I apologize because I created it and it's my fault. For those of you who have not yet gotten to work with it, it's going to be great. Don't worry. The basic idea of the OMOP Common Data Model is quite simple. We want to standardize the structure and the content of different types of healthcare data into a common format. This cartoon schematic is just kind of the high-level visual of the OMOP Common Data Model, but I'll take a few minutes to walk through the pieces that you might want to know about. Each one of these white boxes is a table. The table is going to be, it's a relational database model. Each table is going to have its own defined set of fields and data types representing the information that's contained within those domains. Every OMOP Common Data Model instance around the world has all of these tables. That doesn't mean every data source necessarily has populated all of those tables. And in fact, while it might look like there's a whole lot of tables here, as we get into tomorrow's ETL exercise, you're going to see that there's some data sets that are only going to populate 1 or 2 or maybe 3 tables, and that's totally okay. But the reason and the motivation for this data model is because across the world, across all those disparate types of healthcare data that we know about, there are different types of healthcare elements that we'd like to capture and potentially expose to enable for real-world analysis. So this data model is a person-centric data model. So it basically means every unique identifiable individual in a data source, that's going to be the linchpin to represent the longitudinal history of that person's health information. For that person, there's an observation period. That's the span of time that we actually capture information about an individual. Depending on a health system, that can actually represent like the period of time that they live in a particular geography, the period of time that they have insurance, or just the span of time that they're enrolled within an electronic health record system. But nonetheless, that kind of provides you that denominator of person time that we're going to say, what did we observe about a person during this observation period? And the types of elements that we can then observe in those observation periods are things such as death, visits. So when did you go to your GP? When did you go to your specialist? When did you go to the emergency room? When did you go to the hospital? How long were you in the hospital? Conditions, diagnoses, or problem listings, signs and symptoms, drug exposures, procedures, devices, measurements, which can include lab tests and lab results, other observations. The data model can also support capturing free text clinical notes and have extraction through natural language processing for that. We've modeled various episodes to represent regimens of care. This data model can be used for biobanks to capture specimens and other associated information. That's kind of the stuff on the left-hand side, which is in blue. It represents the person-centric view of like what we can capture. To reiterate and reinforce, not every data set has information in all of these tables. Most data sets don't populate many of these tables, but thus far across our community with hundreds of databases, we've learned that pretty much everybody comes to us saying, I've got this unique special data that can't possibly fit in the model. And thus far, it always fits in these tables on the left-hand side. That's the structure, tables, fields, data types. In the middle here, the standardized vocabularies, this is how we standardize the content of the OMOP Common Data Model, by actually figuring out a way to speak the same language, whether or not we're talking about the same language to represent conditions or drugs or procedures or measurements. The OHDSI standardized vocabulary is a relational data structure that contains concepts, which are basically the atomic elements of what we could observe in data sets, and concept relationships, basically being the relationships between two concepts. For example, a drug may have a relationship to a more specific product associated with that ingredient, or a broad condition like cardiovascular disease could be the higher level concept for a lower level concept like acute myocardial infarction. The standardized vocabulary, the basic idea is this becomes our Google Translate between all the different codes that exist in all the different data sets around the world. So in Australia, my understanding is you've got some data systems that are using like ICD-10 AM codes to represent diagnosis. That's AM being Australian modification. That's a vocabulary that only lives here in Australia. So that's great that you have it here in Australia, but if you wanted to perform some sort of analysis in Europe or in the US or somewhere else, they're not going to have those codes. So how do we figure out how to translate between what you've got here in Australia and what I might have in the United States, or what a colleague might have in the Netherlands or Korea? The standardized vocabulary provides us a way to take source codes, such as your ICD-10 AM diagnosis codes, and map them into standards, which basically become the referent language that we use for each of those clinical domains. So for example, we use SNOMED as a standard vocabulary for conditions. We use RxNorm as a standard vocabulary for drugs. We use LOINC codes as a standard vocabulary for measurements, etc. By choosing some international accepted standard, it actually kind of doesn't matter what the standard is. It just matters that everybody agrees to use a standard, because then we can speak the same language across all of our databases around the world. Now, importantly, when we have this data model, you don't lose the information you started with. If you had a code in ICD-10 AM, you're still going to have a record, and it's still going to have that exact ICD-10 AM code sitting right there in your data set. What we do is we augment that piece of information with this standard code, because that's going to allow us to speak the same language when we think about performing analyses across different databases. There's other elements here that I actually won't get into, but the main thing there to reinforce is that we are going to focus on the OMOP Common Data Model today and tomorrow. What's most important about having any data standard is just that everybody's got to agree to use the same data standard. That becomes kind of your like entry point to be able to perform any sort of subsequent analysis to be in a consistent manner. So at this point, the OMOP Common Data Model is the most widely adopted observational health data standard in the world. That's shocking to me, but it's interesting to see that now there's over 540 different databases that have been converted to the OMOP Common Data Model. That's 54 countries and 12% of the world's population, conservatively estimated, that has data that was in some original source and has been converted into this OMOP Common Data Model format. Now, a couple things I want you to take from that. Lots of people have done it. So for those of you who have a database and you're wondering, is it possible for my data to get converted? The answer is yes, even though I may have to like drag you along for the journey, but it is definitely possible because everybody else starts believing that their data is unique and special and can't be done, and then magically ends up having it done. But the second thing is probably most important from my vantage point is when we start talking about standardizing now more than 12% of the world's population, now we're not just talking about opportunities for using data, but I would actually assert we have obligations and expectations to patients around the world of what can we learn given that we have 12% of the world's data populated. And so part of this data standardization process is the journey to get to this point where we have data, but ultimately it now puts an onus on us to be good stewards of that data and to use it to its fullest to generate reliable evidence that can actually inform clinical care and health policy around the world. Show a couple examples of projects that are going to be interesting and relevant for this conversation. One of the projects that I had a privilege of leading as an industry lead was something called the European Health Data and Evidence Network, or EDEN. The idea of the EDEN project, this started 6 years ago now, and is now since completed. At the time, in Europe, there were lots of different electronic health record systems, inpatient and outpatient systems, some national registries in Scandinavia, but many stakeholders, including the European Medicines Agency, lamented the fact that it was super hard for people to learn across data in Europe. In fact, the European Medicines Agency, responsible for monitoring products across Europe, basically had published multiple papers saying, we don't even have access to data for the most of Europe, and it's not possible for us to actually actively monitor medical product use and adverse events and very basic things. In this project, we sought to try to see, can we identify many different data sources across Europe, and can we standardize them to the OMOP Common Data Model? And over the course of 5 years, we identified 208 different databases, gave them a little bit of seed money, and gave them instruction and training on how to go through the process, like the training I'm going to give tomorrow on the OMOP CDM ETL. Train some small to medium enterprises to like provide technical support, and had them go off and see whether or not they could get their data converted to the OMOP Common Data Model. At the start of the project, I would have told you that I would have thought the project would have been a phenomenal success if we had identified like 50 databases in Europe, and if 25 of them had gotten all the way to the point of having the OMOP Common Data Model. I would have thought that that was like a giant success. Instead, we got 400 databases that applied to be part of this effort. We could only fund 208 of them. And of the 208, 207 of them successfully completed their OMOP Common Data Model instance at the end of the project. And the last one finished up a little bit later. So despite the fact that this is representing all of the countries and all the different databases that we converted, any different type of data you could imagine, whether it be biobanks and electronic health records, inpatient, outpatient, claims, specialty registries, oncology data sets, what have you, all of them went through this journey of standardizing their data. And as a result, created an operational network across Europe that now could become accessible to generating a lot of evidence for Europe. And, and explicitly, the EDEN project has now laid the foundation in Europe for regulatory systems that are used by the European Medicines Agency. There's a project called Darwin EU. There is now industry-based networks that are using these data sources, and these individual countries have now established their own form their own research consortia that are all based on the OMOP Common Data Model, and they're being extraordinarily productive in generating lots of evidence. And this all happened in the course of basically a 5-year research grant that we had. Now, I mentioned the OMOP Common Data Model having this component of standardizing standardized vocabularies to provide us a common language. This is a public resource that we create in the OHDSI community and make publicly available. You don't need to create the vocabularies and the mappings. You just need to download them off the OHDSI website. What you actually download is a set of tables, the concept table, the concept relationship table, the concept ancestor table, that contains the content for all the vocabulary terms, both source non-standard codes, as well as those standard codes for all the clinical domains of conditions, drugs, procedures, measurements, what have you. So that represents, when you go download this thing, you're going to get a data file that's going to have like 11.8 million concepts, of which 3.7 million of those are standard concepts, and and the rest of them are non-standard concepts, and all of the relationships between these conditions, drugs, procedures. Just to like give you kind of a schematic, this little tree map here is showing you kind of the composition of which vocabularies make up things. I'll point out like AMT is your drug codes. So like they're already in the OHDSI standardized vocabulary. If you download it now, you can get those. And you can see that that's one of many different drug vocabularies that are represented in our non-standard space. And it's a relatively small fraction of the overall vocabulary, but it's in there. Now, importantly, this is a global community effort to continue to evolve and maintain this vocabulary. So as we grow as a global community, we identify more vocabularies that need mapping. And as a community, we create those mappings and we make it part of this public resource. One of the things I'm hopeful that comes out of our collaborations in Australia is that, like, I understand you guys have ICD-10 AM codes that need some, it's not going to be a hard job, but some of that's going to need to be mapped to SNOMED. I understand you guys have like Archie codes that are in, you're using for procedures. We need to map those into standard procedure codes. I understand that you got a lot of free text that's going on for your laboratory measurements. We're going to want to be able to map some of those things together. And then AMT's one of your drug codes that's already there. But this should not be the case that each one of you who's going to go down the journey of converting data should be thinking, oh crap, I need to actually figure out how to map my vocabulary. It should be the kind of thing that, like, together as one Australia research consortium, we create one mapping once, and everybody benefits by using that resource. And indeed, this entire OHDSI global community is stewarding this entire vocabulary, keeping it refreshed and up to date, and posted every 6 months with new content from all of the vocabularies around the world.
Patrick, can I ask a question about that? So that vocabulary maintenance, who does that, and is it funded? Is it sustainable?
That's a great question, Roger. So the Central Coordinating Center at Columbia University, where I work, we are the responsible for this vocabulary. We fund a vocabulary team. Many of the folks are currently working at EPAM, Odysseus, who actually are vocabulary terminology experts. Plus, there are other individuals in the community that contribute their time to this effort. Columbia currently pays basically half the bill for it, and currently Erasmus MC pays the other half of the bill for this. We are looking for additional sustainable sources of funding to continue the vocabulary work. I'm actually putting together a very large European grant, like another continuation of Eden, for 5 years that would put a lot more money invested into the vocabulary work. So I don't worry about the risk that it's going to disappear, because everyone's dependent on it, but it is something that want to be mindful of the fact that it requires continuous maintenance and it's a continuous support, because it's a living object. It's not a one-time activity.
Yeah. Oh, thank you.
And like order of magnitude, just to let you all know, it's like it costs us like $500,000 a year to maintain the vocabulary and make it freely available for everybody.
Oh, interesting.
All right. So the other element of how we work in OHDSI is we work as a distributed data network. What this explicitly means is that organizations who have their data, so any of you who are going to be here for the ETL, you've got your data, it's in its source schema. It's got its own set of tables, fields, structure. You go through a process of standardizing the data to the OMOP common data model, which means you're going to develop some sort of ETL pipeline. You're going to write some code. Maybe it's going to be some gnarly SQL script that's going to point to your source schema, and it's going to spit out a destination schema, which will be the CDM schema. And then you have this new relational database that's sitting in your environment. At that point, analysis code developed by anybody can basically have code that just points to a database, which it's known to be the common data model. That code is going to manipulate the data in the data model to produce statistical analyses and generate only aggregate summary statistics that are shared back. As an open source community, we do this only through open source software. Right now, we're primarily developing like R packages. So we write an R package that does something like a characterization analysis that basically says, tell me how to connect to your database. The input will be your database, the specification of what I want to produce my characterization about, and the output will be aggregate summary statistics that come back. By being a distributed data network, it means every data partner can download the code, run it securely within their own firewall, look at the results, share back the aggregate statistics, and then the aggregate statistics from all the sites can be compiled together into a meta-analysis to produce the final result. What that means is you never ever share patient level data between any institutions. And so we've actually shown for all those three use cases, characterization, estimation, and prediction, that we can produce the exact same results as if we had compiled all the data together in one centralized place without actually needing to do any of that sharing of the individual patient level data. And this is very important for like protecting patient privacy. And it imposes a rigor of how we think about performing analyses, because now we can no longer have the meandering journey of the researcher who like picks and prods at the data because they don't even have access to the data. You've got to be able to write an end-to-end piece of code that's going to go to the database, perform the whole entire analysis, and come back with the aggregate result. That requires real discipline for anybody who is mostly doing like your meandering code, like I have written quite a lot of in my life. It's way harder to think about. I've got to write a function that has an input and an output, and I need the code to actually run end-to-end without any human manipulation. At the same time, by imposing that rigor, it means that we can actually satisfy all those system requirements of reliable evidence that I mentioned earlier. So I talked about the three different types of complementary evidence: characterization, patient level prediction, and population level effect estimation. These are three classifications of different types of analysis that we spend a lot of time in the OHDSI community on. No one is better or worse than another. Many types of analyses, many types of studies we do actually involve multiple or all of these. But the important thing to think about is, what is the evidence that we actually want to generate? What's the research question that we want to ask, that we want to get a reliable answer to? By standardizing data, it allows us to standardize our analytics, meaning that we can write those R functions that are going to perform the analyses that we want. And in the OHDSI community, we've built quite a large library of these R functions so that we know we can perform all these different analyses. But one of the biggest insights we've actually gotten wasn't about standardizing the data. It wasn't about creating standardized analytics. It was, how do we get our research community to think about standardizing how they ask questions? And in fact, one of the most simple things that we've done that's actually been most impactful is aligning the community about how to ask questions in a consistent, reproducible way, such that we can take advantage of standardized analytics that have standardized inputs, will produce standardized outputs on standardized data. And so just to illustrate what this table is showing you is, we've tried to standardize how we can ask particular types of questions like characterization, estimation, and prediction by creating fill-in-the-blank templates where you can just ask the question in a consistent manner. For example, here, if I took the one in the middle here, safety surveillance, the question generically that we might want to ask would be, does exposure to some drug increase the risk of experiencing some outcome within some time horizon? And all you need to do is, now that I've got that question with the fill in the blanks, I could fill that in to say, does exposure to ACE inhibitors increase the risk of experiencing angioedema within 1 month after exposure start? By specifying that research question in this consistent format, not only have I asked a well-specified question, but now I know which tool I can go grab, what are the inputs to that tool, how is the tool going to run to answer the question, and I know exactly what the output is that I'm going to get as a result of asking that question. And as a community, we've worked really hard to try to formulate this way of thinking about standardizing the way we ask questions, such that we can build open source tools to standardize how we actually deliver the evidence in that space. That's not to say that we are anywhere near done with building open source tools, because we'll continue to evolve this library of capabilities, but it really has been I think a pretty large change in how we think about the systematic approach to generating evidence at large, which goes beyond, like, when I started, I just like come up with a random question and write a random protocol and then maybe like figure out how to code it afterwards. This is a much more disciplined approach to take to think about the evidence we want to generate. Oh, I mentioned tools. For anybody who is interested in developing tools in our community, we've got a wonderful group of open source software developers. We have an ecosystem of over 40 R packages. More than half of them are in CRAN. So like if you are an R developer or if you're an R user, you can just like open up a library and you can download these packages. They have been downloaded collectively over 1 million times and are heavily used. And we've used these to publish hundreds of papers at this point. So one of the real values of being able to use standardized tools is that you are not going to have to go reinvent the wheel of how you figure out how to program a logistic regression. There's going to be a package that tells you how to do propensity scores that you're just going to be able to call and rely on to generate the evidence that you want. And I mentioned scholarship. So we pride ourselves very much on trying to actually not just advance the science, but actually produce scholarship. We've published over 900 articles as a community, and this tar ball is actually representing all the collaborations that happen. One of the things we believe is that science is a team sport. And so that means to generate reliable evidence, we need lots of data partners. That means we need the people who did all the work to ETL the data, working together with the clinicians who have the questions, working together with the analysts who are running the statistics, that together we're sharing in the enterprise of this joint evidence generation and dissemination. And we have lots of very large collaborations where like a success could be a paper that may have, dozens, or I think we've got one paper like with over 100 co-authors, because that's what it took to actually generate some of the large scale evidence that we've produced as a community. And actually, Nicole, I don't remember where you are on the picture. Do you know where you are? You're one of the big dots somewhere, but I don't know. Let's see. There's our Korean contingent over here. You're going to be somewhere over there. Let's find you. Somewhere. Nicole's a big dot somewhere. I'll just say that. She's a leader in our community, publishing lots of papers.
Patrick,
Yes.
just while we're on the subject of career, most of our public hospitals are now using the OHDSI common data model. Is that correct? It's fairly widespread in Korea, that's my understanding.
In Korea, yes. So in Korea, they have largely created an entire nationalized system where 80% of their hospitals are using the OMOP common data model. Their large national claims databases are converted to the OMOP common data model, and they've created a trusted research environment where basically any researcher in Korea, if they develop a protocol, can run the analysis across their entire feeder net network to perform analysis. So it's a really inspirational model of what they're able to do in Korea. That we oftentimes hold up as even here in Australia, we can learn a lot from what's actually happened in Korea in terms of thinking about how would you bring together your states and territories with the Commonwealth data and put that all together as a common resource. Yep.
So when it comes to the common data model and how you said you'd write an R script and then you access it and give you an aggregated result, what do you give the users to write those R scripts in terms of knowing what the common data model will look like or how to scrutinize it and what the volume is?
Yep, that's a great question. I'm going to use this slide to answer. No, this is perfect. I was going to use this slide to actually answer your question. So in OHDSI, we're collaborating on 4 things. Open data standards, that's the OMOP common data model and the vocabulary. Open source development, so that's going to be your writing the R code. We collaborate on methods research, so that's like figuring out how to make the R code work, like what's the right statistical model to use, and then clinical evidence generation, like asking the real questions and answering them. So the functional way that this works is every data partner converts their data to the OMOP common data model. So they have their source data, they convert it into this database. I'm drawing this literally as a database. This is a relational database. Got your data in Postgres, Oracle, SQL Server, Databricks, Redshift, whatever you guys got. It's a relational database with a bunch of tables and fields. Inside of that firewall, they're going to download an R package. So that means like somebody in the environment is going to have RStudio session opened up. They're going to download an R package. They're going to have a connection string to the database, and then they're going to hit run. What the code's actually going to do is through that connection string, it's usually going to serve up SQL statements to the database to manipulate and create a data object, then bring back usually some sort of analytic data file to R to run statistical models. And then the output of that overall R package will usually be some sort of like output CSV files with the summary statistics, for example. And then so that package that's run will ultimately generate result objects like CSV files. Those CSV files, so like if I write a network study, so I've written a protocol and that's where I write my R package, sites will download the package, run it, and then what's going to be shared back are those CSV files. I'm going to load them into a central relational database, Postgres instance somewhere. I'm going to be able to compile results from different sites, aggregate them together, run some sort of meta-analysis. And at that point, I'm going to be able to like interpret the summary statistics and write a paper or what have you.
Mhm.
That makes sense?
I'm still new to this, but yes, kind of.
Okay. So the big distinction that's different from how I was classically trained to do analysis was like, I had my environment. I was like a SAS programmer back in the day. So I had like my laptop, I had my SAS instance, I had the data locally, centrally like on my laptop. So I was like writing SAS code that would just directly touch the data in interface. First big distinction here is data sits in a relational database, not like in a flat file on your laptop. That means now the data actually can be on some external server, right? It doesn't have to be on your laptop. You can connect to some server that has your relational database somewhere. Then in terms of running the analysis, the distinction between me writing individual commands and calling them, like if I have the data locally, instead I'm wrapping up all the commands I'm going to run into one big long script. And that script basically is going to start with make a connection to the database, perform steps A, B, C, D, E, run statistical models, and at the end, output summary statistics. So you've got to write that whole code to basically do all the things that you would do on that meandering journey. You got to make it work end to end. But if you're able to develop and test that package, then that package can be downloaded from a whole bunch of different sites around the world. They can all just download the code and basically just hit go by putting in their database connection. They can run and then share back those files. That's way harder to write code, but it's also makes it possible that all these sites around the world can actually like run your code because it has to actually work for everybody by imposing these standards.
Patrick, just one thing to highlight, it's in the name common data model. The fact is the common data model will look the same wherever you are. So if you've got one in Queensland, it'll look the same as the one in Melbourne or in London. It's the same common data model. So when you're writing code, you know what the structure is, so you can write the code against that known structure of a common data model.
Yeah, thank you, Roger. Yeah, so as an example, if I were to write SQL code to summarize, and I wanted to know how many people exist in your database, I could write select count star from person table. That code, select count star from person, that code will work in every site around the world, because everybody has agreed that they're going to have a person table and they can do that count. And so my R package could just be the command select count star from person. Everybody would be able to download the package, run it, and they'd be able to return back that value that came back. And it's because of the fact that it's exactly as Roger said, because everybody's agreed to this standard and they've agreed to the conventions of talking to the database, that code, if you can make it work for one common data model instance, it will work for the other common data model instances. Any other questions, comments, challenges? So before you get too overwhelmed, I want to make a point here. Nobody in the world, not me, not Nicole, not anybody in the OHDSI community is expert in all of these steps. In fact, this is a super hard process by itself, which requires us to build a community of people who are experts in different things. So if you're here and you're going to be here tomorrow because we're going to do the ETL and you want to geek out and just think about data standards, you don't care about the rest of that, that's great. There's a place for you in the OHDSI community and we'd love to have you. If you're a software developer and you're like, hey, just give me a data model and I'll write code and I'll make a package work. Like there's whole groups in the OHDSI community that this is what they want to do. They want to hack code for a living and produce cool packages that everybody can take advantage of, and you can be there. If you're a methodologist and you want to think about best practices for causal inference, or you want to geek out on the latest machine learning algorithms, there are work groups where you can participate in there. If you are a clinician or you're working with a clinical group to either perform research or operations on a specific clinical question, you can just come to the community there. If you are somebody who has access to a data source and you just want to contribute to the common cause by being a data node, that's a good way to participate. You can convert your data to the OMOP common data model, and then when these network studies come through, you can just run the code on your data and share back the results. And if you're just interested in like being part of the overall process and help to interpret the evidence and help to disseminate it, like that's also a place that you can participate. Nobody in our community can do all these things. In fact, like this is why we believe it's a team science. Like each and every one of these boxes is an incredibly complex thing, which is why we need to bring lots of different smart people together from around the world. But collectively as a community, we've got lots of really smart people working in every one of these boxes. And it's how we can actually do all of these things together is through this open science collaboration. So in contrast to that picture that I started with, that I said, like, everybody's following this bespoke meandering journey through the process that we don't trust, what we've been trying to think through as an OHDSI community is how can we actually build open science systems that actually can bake trust into the process. And so the picture that I'm going to highlight here is kind of our vision for the world that isn't just speculative. We've now implemented this many times, but I want to walk you through how it's different from the current status quo. We believe that evidence generation should actually be a systematic process, that data sources are converted to some standard, in this case, the OMOP Common Data Model, such that analyses can be systematically applied across a collection of databases. Every analysis should actually have required input specifications, which basically requires specifying what analysis you're performing for what populations and what decision thresholds are going to determine that the evidence is sufficiently reliable. At that point, we want to go through a series of pre-specified stage gate operations to make sure that we can convince ourselves that our evidence is reliable. Step one is to do data quality evaluation, where we actually assess whether or not a data source is fit for use for the question of interest. And if a data source is determined that it's not fit for use, we stop. And we actually say, this is not going to be reliable enough for us to move forward. If there are some data sources that fit for use and we pass that objective criteria, we can move on to think about our phenotype development and evaluation framework, that step of identifying the cohorts of interest in any given study. It is possible, in fact, frequently happens, that despite our interest in a research question, the data doesn't support our ability to identify the exposures of interest or the outcomes of interest, in which case we need to stop and say our data is not sufficient for this question. But if we do have sufficient evidence, do have sufficient phenotypes, then we can move into analysis reliability, conducting statistical analysis on the data and actually assessing whether or not we can actually trust the statistics that we generate. And it's actually frequently the case that we actually learn that we don't trust our statistics. Maybe we're doing causal inference and we see that there's too much residual bias. Maybe we're doing machine learning and we figure out that we actually don't actually see enough discrimination. Or maybe we conduct characterization analysis and we see just too much heterogeneity across our network. If we don't trust the evidence, we need to stop. But if we can prove that we've satisfied all these pre-specified criteria, then we're at the position that we can unblind our results for our analysis and start the process of disseminating those findings, making all of that information publicly available. Reason why we think this paradigm is actually important and significant is because now what we're saying is the task of generating evidence isn't just about generating the evidence. It's about generating the evidence and generating the proof that the evidence should be trusted. And we believe that those two components need to go hand in hand when delivering any sort of evidence to any sort of decision maker. All right. So I'm going to go through just a fun little narrative of a story of a specific analysis that we performed. It's going to give you like a 5-year journey in the course of like 5 minutes of a large study that we did that Nicole participated in called Legend, which was the large-scale evidence generation and evaluation across a network of databases. Legend became kind of a systematic demonstration of this whole open science system for evidence generation that we applied. And we've applied it now to multiple disease states, but I'm going to tell you a story about how this worked in the area of hypertension. So the basic principles that we laid out when we came up with this was that we need to create a systematic approach to define a collection of research questions, systematically apply the exact same methods across all the questions across a network of databases, then systematically generate all of the evidence and share it in a consistent fashion. We identified these principles of best practice so that we're going to generate evidence at large scale. We're going to disseminate everything that we had. We were going to pre-specify all the analyses we performed, apply only best practices, and maintain data confidentiality along the way. Ultimately, we saw this as a model for how evidence generation could be done that we wanted to actually invoke and apply in a consistent fashion to see how well it would play out. So we did this for a specific question, which was looking at first-line therapies of hypertension. So many of you may know, hypertension, there's a lot of different drugs that are available to treat high blood pressure, including different classes of drugs such as ACE inhibitors, angiotensin receptor blockers, beta blockers, thiazide diuretics, large collection of different drugs that are available. If you are diagnosed with hypertension, your doctor is probably going to say you should take a medicine to try to manage that in addition to diet and exercise. And if you do get prescribed a medicine, there is a large collection of alternative treatments that the doctor might consider prescribing you. The question that we wanted to start with was to ask, which one of those many dozens of alternative treatments that are available, which one makes sense to be the right treatment to offer people that be most effective and safest to be used. Now on this picture on the left-hand side, I want to show you, so hypertension, of course, very prevalent disease, one of the most studied diseases in all of research, all of the healthcare research enterprise. And yet on the left-hand side, what you're seeing here is those little dots represent individual drugs for hypertension. And the lines between the dots represent where there existed randomized clinical trials that actually provided us direct head-to-head evidence between two treatments. So if you're a patient and you're thinking like, should I take lisinopril or should I take chlorthalidone? Well, you'd like there to have existed a randomized clinical trial that did a head-to-head comparison so that you'd know which one was better. What you can see, though, is there's very few drugs that are connected with lines. And that's because despite decades of work, there's not actually been that many randomized trials that have given us the explicit answer to which hypertension treatments were better. And hypertension treatments are extremely expensive to run. They can cost like hundreds of millions of dollars. So the fact that all of these drugs are generic means we're never going to get more randomized clinical trials to answer these questions. And so we're kind of left with this limited evidence base. But with real-world evidence, with electronic health record data and administrative claims data around the world, given that there are so many patients in the real world who have hypertension, so many patients who initiated hypertension treatment, it gives us the opportunity to actually use the real-world context to compare every treatment against every other treatment and figure out which ones were most effective. And what's showing on the right-hand side is how many direct comparisons we were able to actually learn from a large collection of databases in the network. And to validate that we were actually generating results, we were actually able to take the clinical trial studies and say, how well did our observational studies produce answers that were consistent with the randomized clinical trials? And actually, on the right-hand side, you're actually seeing the agreement between basically the black line there represents the clinical trial, and the green line there represents, or in this one happens to be green, represents our real-world evidence study. And what we showed was that our real-world evidence matched the clinical trials exactly as much as you would expect if there was complete agreement. There was only 2 examples where there was a slight disagreement, and that's how much you would expect even if they were exactly aligned. So we were really confident about the fact that retrospectively looking back, we were able to show that real-world evidence produces the same answers as clinical trials for this important clinical area, given that most questions don't even have answers from clinical trials. So we presented these results back in 2018, showcased the fact that all of these different drugs that are in the clinical guideline all were suggested as like equally available and good first-line therapies. But there was this one point that was raised in the guideline that says chlorthalidone, which is a thiazide diuretic, is preferred on the basis of prolonged half-life and proven trial reduction of cardiovascular disease. And it kind of bothered us that despite the fact that the guidelines said that all these drugs are equally likely, that they put this one little statement in here, because that statement is not supported by any head-to-head clinical trial that said that chlorthalidone was indeed better. And so we had the results of chlorthalidone versus every other drug, so we could actually see what we would, whether or not we would agree with the hypertension guidelines that are available. And so the way we would think about doing that is if we were to run a randomized trial, what you'd really like to do is you'd like to take people on chlorthalidone, compare them to an alternative drug like hydrochlorothiazide, follow them up after they initiated treatment, count up the outcomes, and then you'd figure out which of the drugs had more cardiovascular events, which would be the effectiveness markers, which ones had more side effects, and you'd be able to use that information to conduct a study. This would be like the desired randomized clinical trial if we could run it. When we're using retrospective data analysis, we can't do a randomized trial, but we can use target trial emulation to design an observational study that looks like this, just taking out the randomization effect and instead use something like propensity score modeling as a way to adjust for baseline characteristics. But it turns out that at that same time in 2018, there was one more clinical trial that was ongoing, being run by the US Department of Veterans Affairs. It was called the Diuretic Comparison Project, and they were comparing chlorthalidone versus thiazide diuretic. And back in 2018, they said that they were hoping to run this study with 13,000 patients. They had started in 2016, and they were hoping to be completed in 2022. So back in 2018, I'm pretty sure, Nicole, you were at this symposium. We basically said, well, we could sit here and wait till 2022 when this clinical trial comes out, or we could go ahead and look at our real world evidence now and decide whether or not we need to act on it. And there was the question we asked, do we wait for 4 years for the trial to be completed? Well, we didn't wait for 4 years. We went ahead and actually published our results, suggesting that actually, and we published this result from the Legend study focused on this comparison of chlorthalidone versus hydrochlorothiazide. And in this paper, we published it in JAMA Internal Medicine, we actually learned that, or what we observed was that chlorthalidone versus hydrochlorothiazide, there was no difference in the effectiveness, even though the guideline said chlorthalidone is probably better. We did not see a difference in any of the markers of myocardial infarction, heart failure, stroke, or composite cardiovascular disease. We produced we had hundreds of thousands of exposures of chlorthalidone and more than 30,000 exposures of chlorthalidone, 600,000 exposures of hydrochlorothiazide. So we had pretty good statistical power to have confidence in saying we really don't think there's any difference between these drugs, even though the guideline says you should prefer chlorthalidone. But not only did we not observe any difference in effectiveness, we actually saw that chlorthalidone had higher risks of certain serious side effects. Specifically, we saw that there was an increased risk of hypokalemia. So if given two drugs, they're equally effective, but one causes more side effects than another, then if anything, I'd actually argue you'd want to take hydrochlorothiazide, not chlorthalidone. And that would go explicitly against the clinical guidelines. So we published this paper and said, hey, the guideline says recommended chlorthalidone. We think that these drugs are equally effective, but chlorthalidone might have an increased side effect profile. Now, we were really confident in this because we developed a large network of databases. We applied all of our statistical best practices using our standardized tools from OHDSI. We had pre-specified diagnostics that gave us confidence that we had adjusted for bias. We had multiple databases that produced estimates so that we saw consistency. We were able to be fully reproducible. We were replicable and generalizable and robust in terms of our analysis. We satisfied a lot of those reliable evidence criteria that we sought forth. And yet, after publishing this paper in JAMA Internal Medicine, which is a good journal, we got this response from some letter to the editor who basically said, hey, we read this paper with interest, but it's an observational study. Observational studies are not to be trusted. And this clinical trial is ongoing right now. We should probably just wait till the clinical trial comes out rather than trusting this crazy observational study, because this is too much at stake. And I don't know if everybody knows, but Paul Welton was one of the authors of the hypertension guideline. Tom Frieden, former head of the CDC. So when these big wigs talk, everybody says, okay, I guess we should probably continue to dismiss the real world evidence. That was back in 2020. So indeed, we can wait a couple of years. And the nice part about this is time does elapse. So eventually the diuretic comparison project study completed. It was published in the New England Journal of Medicine. And what they found, I'll go there. I'm going to show you the cardiovascular profile here. This is our estimates. We said that there was no difference in cardiovascular events, hospitalization for heart failure, hospitalization for stroke, hospitalization for heart failure. The trial showed absolutely no differences between these. We said chlorthalidone increases the risk of hypokalemia. They discovered in their clinical trial that chlorthalidone increases the risk of hypokalemia. So we waited 2 years for them to just verify what we had already said in our prior paper. Tom Frieden, that same person who wrote the commentary saying we should be careful, he actually published this thing earlier last year. where he basically said, hey, listen, we need to get better at evolving how we interpret evidence. And specifically, he said, I was one of the big proponents for chlorothalidone. I believe that it was better, but now there's enough evidence. And he makes reference. There was another large study that used hundreds of thousands of patients and found no difference. If the drug was much better, then it would have shown up even with study weaknesses. So the guy who basically said, we don't really trust this study, eventually said, you know what, enough's enough. We're in a situation where we really should not be advocating for chlorothalidone as a preferred treatment for hydrochlorothiazide. The upside of this story is I am very confident that if done right, we can generate real world evidence that is reliable, that will match randomized clinical trials. We've shown it retrospectively, we've shown it prospectively. And these are not just isolated anecdotal examples. Like this is a case of a disease that is extremely prevalent. Well, I think I saw it, I looked, I think like 25% of Australians are going to have hypertension is the prevalence of hypertension. So you all are going to get a first line treatment of one of these drugs at some point. And it would be useful for us to have evidence to make these decisions. That said, I don't fault Paul Welton and Tom Frieden for saying don't trust real world evidence, because the collective enterprise isn't to be trusted. Even though we put all this rigorous process in place, we're just yet another study in a sea of thousands of studies that aren't necessarily all reliable. So the onus is on all of us to make real world evidence actually be reliable to the point that we don't have to wait for clinical trials, wait for years to actually have impacts on patients, that we can actually drive this work right away. Marcus.
Actually, sorry, half of mine is because I'm being distracted, but what's the difference in sample sizes? I just want to get a sense of what the clinical trial is doing versus what you show.
Yeah.
And it's purely for my entertainment, so
Yes.
I apologize terribly.
Yeah, so
Fans, but it would help make me feel better when I go to sleep tonight.
the clinical trial that took 7 years to recruit, total collected 13,500 patients. Our Legend study had 730,000 patients. So we had order of magnitude more data. We're able to perform the analysis in an order of magnitude less time, and fully replicated the results of the retrospective results and the prospective results. That said, I think there's a lot of, I am not saying we should down with randomized clinical trials. Like randomized clinical trials have a critical role, but most questions are never going to get answered by randomized clinical trials. So the real onus on us is to figure out how can we prove that our evidence is good enough to fill the gaps that exist. The problem is it took them 7 years and I forget how much, but something like $40 million to run that clinical trial. We can't afford as a global society to be running all these studies when there's so many questions that patients deserve the answers to. So I'd say it's on us to figure out how we take our real world data and plug all those evidence holes that exist. But that first requires us to know that we can trust the evidence that we're generating.
Yeah, just the financial arguments hard to.
You guys here in Australia are probably not going to be running a whole lot of
we're pretty broke.
$100 million clinical trials.
Yeah, and there's NHMRC, the funding body, hasn't had a real financial uplift in 10 years.
Yes.
Oh, it's not a question, but the selection of the cohort is very important here about the multimorbidity.
Yep.
How you dealt with that one.
Yeah, it's a great question. So the question is, how do we actually extract out the cohorts and make sure that we make them similar?
Yeah, I mean, yeah, some people may have the different conditions.
Yep. Yeah. So I'll back up. I'll back up a second just to describe a little bit of what we do here. So in our standardized way of us thinking about applying epidemiologic designs for causal inference questions, we commonly will apply a target trial emulation framework where you're designing a study like it was a randomized trial. So we extract out patients who were, back up one more slide. So what we want is a newly diagnosed with hypertension who either initiated chlorothalidone or initiated hydrochlorothiazide. We have some medical history that we have in their data. So that allows us to know what are their comorbidities, concomitant medications, health service utilization behaviors. In a randomized clinical trial, you'd be like flipping a coin and assigning them to these treatments. In our observational studies, we can't do that. So instead, what we use is propensity score adjustment, where we create a prediction model that predicts which patients got chlorothalidone and which patients got hydrochlorothiazide on the basis of their medical history data. And then we match them on their baseline likelihood of those treatments. And so when I showed briefly these plots, this is actually showing us the propensity score distribution. How similar were those groups of people? And this plot is actually showing us all the baseline characteristics. How similar were we able to make those groups after we did the propensity score adjustment? So we're able to actually prove, looking at tens of thousands of covariates, that no variable was very different between these two groups. And that gives us confidence that there isn't some confounding factor that's going on in the analysis.
Other thing is that, so you work on the linked data or?
So in this particular, for this one, this is a large administrative claims data set. This is a different US claims data set. This is an electronic health record data set. So different databases, they're not linked together at the person level, but each data set had information about exposures, conditions, follow-up time to look for outcomes, that kind of thing. Yep. Yes.
So, like, mechanically, how different is a clinical trial versus this retrospective like study in terms of?
Yeah, so the biggest difference is the distinction between prospective data collection versus retrospective analysis. So when you run a randomized clinical trial, what you do is you recruit a patient, you flip a coin to say, I'm going to assign you treatment A or treatment B, and then we wait and follow you, and you have to come back every so often to come back, and we fill out forms to see how you're doing over a period of time. So when I described that VA, the diuretic comparison study, they actually had people who were enrolled in the study, and they had to kind of wait a few years to see whether or not they had heart attacks. When we're doing retrospective analyses of our EHR, we already have the full history looking back for these people. So I can actually perform the analysis right away. I can look back in the data, find people who have taken these treatments, and then immediately look forward to see, do I see a heart attack in the record?
The result is still the same in terms of like how accurate the result is, so long as the acquisition does.
So there's been numerous efforts in the pharmacoepi community that have been able to verify that if we apply best practice designs and statistical methods, we are showing that real-world evidence studies can produce estimates that are consistent with estimates from clinical trials. This was an example where we've done it in the OHDSI community at the network level, but there's also really nice work that's been done by like Shirley Wang and others that has actually shown that, like, as long as you follow best principle practices, like, you can get reliable answers. That said, actually, Sally, you'd be better to speak to this than me, but like, so like most papers that I read in the pharmacoepi community that don't come from pharmacoepi experts, like, they don't follow best practices. So they fall very short of this, and we are worried that they are biased studies. So like, if done well, it can produce a valid estimate, but unfortunately our field at large is sinking in a lot of suboptimal studies.
And I can do this because I do suboptimal pharmacoepi.
That's not what I said.
One of the things that I think is interesting, this is about the sociology of evidence generation, right? And so this is such a beautiful example of how this type of work can be ahead of the game in trials, but we could quote 20, 30, 40 examples where observational studies have not generated evidence that's aligned with trials, which is why people traditionally haven't trusted the evidence. So, so I think it's got to be, there's historical reasons why there's doubters, but interestingly enough, the gentleman that wrote the article, he believed this drug was superior. And because of his lack of faith in observational data, he said, we've got to wait another 4 years. So it's about ensuring that we are lifting the game here in terms of the real world evidence generation. I think it's just a beautiful example, Patrick.
But, and I just had to piggyback on what you said too. This is where I believe there's bias in interpretation of results. Had we shown what Tom wanted to see,
Correct.
He would have said, this is a great study.
Correct.
But it's because it defied his expectation that he was like reluctant to or took a while to get to.
Did you try to publish it in the New England Journal, interestingly enough, your work? Because the New England Journal rarely publishes trials that don't show differences between drugs.
Trying to remember. JAMA Internal Medicine wasn't our first home. I
Yeah.
think we might have
Anyway,
submitted to JAMA first.
I think the
We
whole
didn't submit
thing
it to
is
New England
fascinating.
Journal.
Biosocial studies have been looked up, have been poorly designed or poorly done. It's not so much the method, sometimes the question is the wrong question.
Absolutely.
So
Absolutely.
you need to think like, would I do a clinical trial in a way? So sometimes you're trying to compare things that you shouldn't be trying to compare. And that's kind of, even before you get into the methods, your question is wrong.
And sometimes you need to learn that when you ask the wrong question, the data will tell you that you've asked the wrong question, but a lot of people just keep going anyway.
Right.
So with our diagnostic criteria, sometimes if you ask a wrong question, the data should tell you you've got a wrong question, you should stop. But it's a very natural tendency that, like, once you started down a path, you want to keep
Like
going.
if you have no overlap because the decision to take drug A versus drug B is quasi-deterministic
Yep.
for whatever reason, then the question is not the right question.
That's right. Adrian?
Another aspect of this balance between interventional and observational studies is that there are a whole set of populations that can't participate in the clinical trial. So you read evidence about intervention or something like that. The only way you can get out is through or children or very young.
Absolutely. Yeah. I mean, if we're waiting for prospective research to answer all our questions, we're going to be disappointed 99% of the time, which, we need to make sure that the evidence that we generate through our retrospective analysis is reliable. But I think it's the only path forward to actually answering the questions that are on the table, because there isn't somebody else out there that's going to be able to fill these evidence gaps if we don't do it.
It's also a question of data size, as you show. We're never going to have a clinical trial with 100,000 people.
All right. So I'm
There's
just going
another
to,
question
yeah,
up here.
yeah,
Patrick.
please go ahead.
What would be the order of magnitude of, say, the funding required to run a real world evidence around?
Nicole, can you tell him how much it costs to run the Legend study?
To me personally.
How much did I pay you to participate in the Legend?
I wish it was $1 million, but no, zero.
How much did you pay me to do the study?
Zero.
How much did anybody get paid to do the study?
Zero as far as I'm aware.
This entire study we did as a free open science community study.
Yeah. And
Everybody participated because they believed in the question, because they believed in trying to generate evidence. That is not a sustainable business model for the world to do studies. But to be clear, it isn't this can be done because of the fact that all of these sites had already had their data converted to the OMOP Common Data.
So that's the
Standardized
investment.
tools were already in place. So what it meant was we had to get together as a group, write a protocol, write the package, get sites to run it. Running it, took some compute cycles. Then we had to spend our own time to write up the paper. I don't want to belittle the fact that's real work, and that's hard. And many folks need funding to allocate their time to do that type of activity. And I don't want to belittle that at all, but this is no longer a scientific/technical problem. It used to be that you'd have to give me money just to even make this thing happen. We are running on a routine basis many studies like this that are basically the reason money has to flow between stakeholders is just because people need to buy out their time to participate. But otherwise, the technology and the science behind this is we're doing a really good job of making it possible for any researcher like yourself to come with a question, come to the beginning and run a study like this.
At the marginal cost of zero per study.
Hmm.
So, what's holding up running zillions of studies, for example?
So people need to be able to allocate their time, and so that every stakeholder group has differences about that. I would actually, Nicole, I'd be interested for you to answer this from your impression. I'd say what I've observed is the OHDSI community has marvelous data standards people, great software developers, good informatics people. relatively speaking, we're lacking in clinical experts who have really interesting questions. So very often we're like pulling teeth to get people to come with good questions to the community. But when people do come with clinical questions, there's a lot of people that want to jump on and help. So I don't see there's any real technical barrier to us running lots more studies, but I do think that there's a resource capacity in terms of like people's time to initiate a study, design, and execute it. But Nicole, you probably have a better answer than that.
Yeah, no, I completely agree. One of the barriers, I think, is the exact point you made about the clinicians being involved. So, you know, we're techie people, we can run this stuff, we can generate it, we can create it. But what we can't always do is see how it's going to help practice, see how it's going to improve practice, who wants to consume the knowledge, you know, who wants to actually, I mean, how should we pitch it to them? And that's a hard thing to do. So, you know, this whole legend analysis is sitting there on a website right now. Like you could go and you could write a paper on some comparison that hasn't been done right now, or some outcome that hasn't been done right now. But, you know, you need a group, you need a clinician to help you do that. And I mean, I'm guilty of writing draft papers and they're still sitting there in my drafts. They, you know, they don't get published because you're on to the next thing and life's busy and you get to the next thing. So I think there's just a people problem in getting some of this information out. It's not a technical problem so much anymore.
I will say though, I will add one thing though. If anybody's seeing this and either is feeling overwhelmed because it seems like a lot, or think that I'm a snake oil salesman and like I'm making it sound too good to be true, everybody is very intimidated by initiating a network study because they think, like I show you these results, they think like, I couldn't possibly do that. Who am I as this one individual? I'm thinking specifically in Nicole's lab, Jack was a spring chicken PhD student and Nicole said, you're going to run a network study. And he like wet his pants. And then we said, okay, Jack, let's do this.
You might be online right now.
Jack, are you online? Are your pants dry? But Jack jumped in, led a study, and published an extremely impactful analysis that looks at fluoroquinolones and aortic aneurysm. If it wasn't for Jack's leadership, he pulled together sites from all around the world, and we ran a study in that's BMJ.
That's a BMJ.
BMJ paper that the PhD student who was like scared to take this on was able to drive forward in a like less than a year and produce an extremely high impact clinical journal. Now, Jack is an extraordinary scientist, but like it is possible for anybody who starts at the point of doesn't know anything and is overwhelmed to actually jump in and lead. But it requires a little bit of a leap of faith that like participating in this open science community effort is a very different thing than like going off and toiling and doing something on your own.
And Patrick, I think the other point about Jack's study, which is critical for people to understand, is he didn't leverage Australian data in that study, did he?
No.
So that was another major misconception that I had when I was learning about this. I thought I needed to offer something, so I needed to have data to contribute to the enterprise and what have you. But it turns out Jack's come up with an idea, and this was run in other jurisdictions without the requirement that even his own jurisdiction contributed data. And I think that's a really important point.
Make a comment following Nicole's comment about clinicians having to come up with more questions or not. I think maybe a good idea would be to think about it when new clinical guidelines come out. Maybe this is an opportunity for the OHDSI community to run stuff. Or the new version or something. I don't know.
Yeah, no, that's I totally agree. I think the guidelines come out, it allows us the opportunity to ask the question, do we trust these guidelines? And when guidelines are being developed, that's an opportunity for us to reach out to the guideline developers and say, like, what do you need to know? And then we can fill some of those evidence gaps. So, you know, I'm an advocate of trying to get us to do a lot more of this. One of the things that I find is the deficiency for myself is like, I don't know the right questions to ask. So I really need to leverage the community to figure those out. But I know that, for example, when we did this work, I went and did talk to many of the hypertension guideline developers. their first immediate knee-jerk reaction was, there's lots of randomized clinical trials. I'm not going to trust real-world evidence. So like, it's just not part of our ecosystem. And it took some while to get them to think, well, if the evidence doesn't exist from randomized trials, what are you going to base your decisions on? The current guideline, it either is there's evidence from randomized trials or it goes straight to expert opinion. It's like, clearly we could do better than that. And so I think that there's a large education effort we need to do in the guideline development community, but it seems very obvious to me, like that's a place where our work can have direct impact.
Well, and it's not just clinical, it's the policy level, and
Yep.
and Darwin and C-Nodes and others are great examples of where policymakers are throwing questions to address. So they may need to be refined, but they're there and they're.
Absolutely.
That-
Particularly, pharmacoepi, like, drug side effects questions. Regulators asking these questions all the time. We're worried whether or not some drug causes some side effect. When they ask those questions, they don't have a plan for getting evidence for it. Those are opportunities to
Right.
go fill those evidence gaps. I'm just going to finish one last motivation. If I haven't motivated you enough yet, I'm going to tell you why OHDSI needs Australia specifically. So there's this this prosperity index, which basically tries to rank all countries on how important they are and how what their total value on multiple dimensions are. Australia ranks 15th out of all countries. I think they're the second in the Asia Pacific region. New Zealand's beaten you overall just by a little bit. Sorry for that. I didn't make the rankings. But what's interesting, so like Australia and New Zealand representing this area as countries that in general are seen as quite prosperous. One of the dimensions, this one right here, the little heart, this represents quality of healthcare, and Australia is ranked 21st in all countries. Despite conversations I've had with many of you about how dysfunctional the Australian healthcare system is, I'll just want to point out that the country that I'm from ain't on this list. We ain't in the top 15, and we sure as hell ain't in the top 20 of healthcare systems. So me as an American, we're spending the most money on healthcare, and we've got some of the worst outcomes. We need to learn from you all about what you're doing, how you're doing it, and how you're actually delivering high quality care so that we can improve our healthcare systems. But all countries need to learn from each other. And, when you see that Australia, you're doing really well, but on many dimensions, like the Nordic countries have better healthcare systems, there may be opportunities to say, well, what are they doing that's so unique and differentiated that could actually improve things? So OHDSI needs to learn from Australia because you guys are clearly doing some things right and doing a lot better than my country. But I also want to make an argument why I think that you guys need OHDSI and the rest of the world. This was the ABS statistics that I pulled, I think are the latest of your population sizes across all your territories and your overall population of 27.6 million. I'm a statistician, so I think a lot about statistical power. And the challenge that I have for all of you is that even if you had a complete capture of all of these patients, you still have a relatively small population in each of your states. Even if you aggregate it together across the country, 27 million is a pretty decent sized cohort. But the moment that you start asking questions about a particular disease or a particular medical intervention, 27 million gets pretty small pretty fast. And to quantify that exactly, I've done this analysis that I'm quite fascinated by. I think some people get bored by it, but I think it's pretty fun. I took the 1,000 most prevalent drugs in the United States, and I plotted them on the y-axis here from like the most prevalent drug is COVID vaccine, all the way down to the 1,000th most prevalent drug. And then I took the 1,000 most common conditions from 1 to 1,000. There's a most common being COVID disease, all the way down to massive right breast. And what I'm showing you on this heat map is the incidence of every drug outcome combination. So like, let's just say a simple question you want to know is like, how many people took the drug and then had the outcome? Because that's what you would want to do if you were going to study side effects of a drug, for example. So what you're seeing here is in the top green, those are the situations where there's a drug outcome pair that occurs in 0.1% of a population. Then you've got, these are all order of magnitudes. Light green is now 1 in 1,000, or 1 in 10,000, 1 in 100,000, 1 in a million in the red. This matrix is 1,000 drugs by 1,000 outcomes. So multiply that together. That's 1 million hypotheses. And you're asking the question like, what's stopping us from doing zillions of studies? I won't say zillion, I'll just say 1 million. What's stopping us from doing 1 million studies? I would say we want the answer to every one of these 1 million studies. It's a reasonable question to ask. Does drug X cause outcome Y for every one of those 1,000 drugs and every one of those 1,000 outcomes? Patients deserve the answer to that question. And yet, given the prevalence of drugs and outcomes, just back of the envelope calculation, you guys have 27 million people in your country. That actually means across the 1 million questions that we would want to ask, there's only about 10% of those questions that you would actually have enough statistical power to actually produce an answer for. So 90% of questions, if Australia tries to answer them, you will not be able to answer them with sufficient statistical power. And even if you had this, 70% of questions, or sorry, 10% of questions you'd have sufficient sample, 70% of questions you wouldn't have sufficient data, and you would need to basically run some sort of international study for. That said, learning something from Australia in combination with colleagues in Korea, in combination with colleagues in Europe, in combination with colleagues in North America, now we can run studies that aren't 27 million, but are actually hundreds of million. And suddenly then, from a statistical power perspective, we actually have enough data to answer questions that you won't be able to answer by yourself in Australia. And so I think you guys are in a really unique position in that, like, there's a lot to be learned in Australia, but I also think that there's opportunity for you to think about how much more you could learn if you don't just do things in Australia, but actually you really think about your role in the international community and how you could bring your Australian questions to the rest of the world and leverage your data in combination with the rest of the world to answer a lot of these questions. So hopefully, as you are thinking about research questions, you won't just think, what can I do to study my state's data, or what can I do to study Australian national data, but you think about, like, how can I answer this question for the world, and how can I start with my leadership here in Australia and then bring it to everybody else?
Personalize the question.
The harder it gets, yeah.
It's impossible, yeah.
Yeah, this is like first order effects, and you're already 90% of the questions you can't answer with your population. Yes.
I would imagine, so I'm a proponent of Sol clinical trial view, would argue that controls are better in prospective clinical trial. However, having said that, have you, by looking across these multiple retrospective studies, have you found how these uncertainties mitigate over larger population?
Yeah, it's a great question.
Like I said, central tendency.
Yeah, it's a great question. So one of the reasons we actually argue for these like legend principles is because if you look at the current publications that come out, there is rampant publication bias. Most things that are published are statistically significant. There's rampant p-hacking going on. Things magically get exactly 0.05, which people have like gamed the system to get that answer. There's massive disproportionate reporting where like people are more prone to report increased risks rather than decreased risk. So we don't know how much null effects. Within the legend principles, when we run all the analyses, there is no p-hacking, there is no publication bias because we share everything. And when we see that, the nominal operating characteristics start to reveal themselves. Most drugs don't cause most outcomes. Most drugs are pretty benign for most things. So we should actually expect that we would see null effects for most associations. But the only way you'll see those null effects is if you actually communicate and report everything, not just cherry pick the things that have p less than 0.05 as we're accustomed to doing. There was this beautiful paper, a little bit of a tangent, but it's relevant here. The beautiful paper came out last week or 2 weeks ago in Lancet. They looked at statin therapies and the safety of statins, which is a drug for high cholesterol. The product label for statins, so this is drugs like Lipitor, like atorvastatin or Lipitor. The product label lists 68 side effects. In Australia, you guys don't have direct consumer ads, but your friends over in New Zealand have direct consumer ads like we do in the US. And if you watch one of those commercials, it's like, take this drug and it'll be great, but then I'm going to list out all the bad side effects. So statins have this product label that has 68 side effects. And what they did was they did a meta-analysis of all the clinical trials of statins. And they performed a statistical analysis to see how many of the 68 things that we're warning patients about are actually have evidence to support them. And they found 4 of the 68 outcomes had a statistically significant increased risk. 64 of the 68 outcomes, they did not observe any increased risk at all. And their conclusion in that paper was, we're probably doing more harm than good by warning people about all these side effects if most of them are not actually true. And like, instead, we'd be better off communicating the 4 things that matter and making patients pay attention to those rather than communicating 68 things that are nonsense. The reason why I share this is meta-analysis of clinical trials, but the reason why I share this is why we currently have a duty to warn about harms is usually a randomized trial was run, insufficiently powered, and there's a numerical imbalance. Treatment group had 2 cases, comparator group had 1 case. Because it was a 2 versus a 1, it's not something that's statistically significant, but out of an abundance of caution, a product manufacturer or regulator may say, let's say that it might be true. That results in a large litany of these adverse events being recorded. But because there's never going to be future clinical trials, we'll never be able to dispel the risk. What real world data offers us the chance to do is say, well, after a product's been on the market, we could actually study the effects. It's equally important to me that we discover real side effects and warn people about increased risk. It's just as important that we actually say, you shouldn't be worried about this adverse event, because now that we had robust samples and adequate power in a well-controlled study, like we actually could discharge this uncertainty that the clinical trial introduced. I think that's a huge opportunity. And if that, I don't know that I trust everything in that Lancet study, but let's even just say it's like half right. They said 94% of adverse events aren't true for statins. Let's say it's only 50%. That still means every other side effect in the label is nonsense. Like, we're doing harm to the public if we're warning about a whole lot of things, but we don't currently have a mechanism to generate the reliable evidence to discharge that uncertainty. And I think an international network of data sources could be the absolute perfect source that we could take those questions and say, indeed, there was a numerical imbalance in this trial, but Sally ran a study and it produced a relative risk of 1.01 with a confidence interval from 0.95 to 1.05. So probably not a risk. And even if it is, it's not something that should change your benefit risk calculus. That's something that's directly within our grasps right now if we collaborate as a network on that type of question. And that's very straightforward for us to do, given all of the standardized data and analytics we have as a community. Yeah.
I have a question. So you guys have OMOPs the entire Korean data set?
I haven't personally, but Korea have. The
Right.
Odyssey community has, yes. They're one of the world leaders.
Well, and how long an undertaking was that for them to transition onto a fully converted OMOP?
That's a good question, Patrick.
Yeah. So in Korea, they have lots of different academic medical centers, like hospitals, that each one did their conversions. And then they also had a national claims database that had the whole country's, all of their reimbursement records. So the time to do an ETL varies by specific thing, but it's order of magnitude. Some data sources got converted in a month, some got converted in 6 months. When they did the national claims data, it was actually during COVID, and they did it in a crisis thing, and they actually did something remarkable. It was done in 2 weeks or something like that. We're going to do a lot more discussion tomorrow about the ETL process, but the one thing that I'll reinforce things is it sounds like it's a big deal to standardize your data, and I don't want to belittle the fact that it is real work to standardize your data, but you need to think about it as it's a step to get to the evidence, and we don't want the perfect to be the enemy of the good. So we want to actually get to the point where generating evidence quickly. I have not personally encountered a data set that I can't get an 80% good ETL done in under a week, but there's a long tail of 80% good to 90% good to 95% good to 100% good. We have lots of organizations that could take upwards of a year to do their ETL, but that is not 100% effort focused on it. That's usually people, diddling on it a couple hours a week and being distracted. But we'll show tomorrow actually using some of the tools, and Danusha's done a great job looking at admitted patient care, APC, and the pharmaceutical benefit scheme, PBS. These are data sets that effectively are like single tables with a bunch of columns. It's like, we'll write the ETL for those tomorrow together because it's not that big of a deal. It's like, order of magnitude, it's gonna, you get what you can get into it, but it's not that big of a deal. It's not something that should prevent you from wanting to do this. It's more like you suck it up to make the upfront investment so that you get the value out at the end.
Patrick, the other thing that's very unique about Korea is it's heavily based hospital only care.
Yeah, that's true.
And specialized clinics. So the system is set up very differently. And I'm not suggesting that it's that reason is the only reason that it's done, but their data is phenomenal because of the structure of that system, which is ours is flipped the other way. We're trying to keep people out of hospital and so on. So I think the reason it's so good is not only because everyone's come on board, but with the nature of the underlying health system that makes it so exceptional. Do you agree with that? Or
absolutely. Yeah. I mean, Korea is a remarkable place in lots of ways. What I found in our collaborations with them, they've been a true leader in our OHDSI community for quite some time. They are almost never the innovator, but they're the early adopter, and then they do it better than everybody else in like everything that's going on. And so they were not the first to say we're going to make a strategic investment in the CDM, but once they did, they made like the most efficient investment of it. And part of it was getting all of the stakeholders like bought into this idea that they were going to do it together, and then like all making this joint commitment, like this is something we're doing together, and they all ran like kind of in lockstep, which was like really remarkable. I agree with what Sally's saying. Like, it's fascinating to me that like they don't really have incentives to kick people out of hospitals in Korea, which I learned about. So like people will stay in the hospital for like weeks.
Yeah.
And it's just like so like I was looking at the AIHW hospital statistics, and so much of it's focused on length of stay, and
Correct.
it's bad if you have longer length of stay. And like the numbers in Korea, like
More like
somebody being like in the hospital for 16 days just because like they're not feeling well is like a very common thing there. So it's like really wild.
And question,
Please.
how much of the ETL conversion can AI learn to do, and are there any studies on the accuracy of that?
That's actually not a random question. That's a great question. So in the OHDSI community, there's lots of different people that have been actively investigating how we can use AI assistance to build ETLs. The OHDSI Europe Symposium is going to take place in April, and I just reviewed all the abstracts that were submitted to it, and there was something like 14 that were specifically on this, like how good is AI at writing ETLs? I don't think anybody's done like the authoritative, definitive answer, but what is remarkable is the new like reasoning models that are grabbing stuff off of line. There's enough public resources about OHDSI and the OMOP Common Data Model. You get really pretty good, pretty impressive starting points. What we're going to do tomorrow is actually talk, and I want to be responsive to your question, but I'm going to shape it a little bit. It used to be that people were really focused on how do I code my ETL? And we've tried to shift the narrative away from the problem of coding it and towards a problem of designing it. How do you make sure you make the right business logic for where the data goes? And then we say, like, given that we've written a specification of what should happen, then it's just a technical task of implementing what you said should happen. So it used to be people would like jump into their SQL console and just start writing stuff and try to figure it out. We said, no. We're going to force you to map each of your source columns to a destination column and write a statement of logic for like what should happen. And then whoever's going to program it has a document in front of them and says like, this is what should happen. Coincidentally, that's exactly what you would want to give an AI to write the code. If you wrote a full specification and then said, write me a SQL script that implements this logic, it's pretty good. It's only as good as the detail that you put in your specification document then. So if you just said ETL this thing and you gave it the source, it's not going to do so great. But if you actually gave it one of our design specification documents, what I've seen, I'm a SQL guy, but I've seen it do it in other languages too. Like, it'll write a pretty good structure as a starting point. I don't think, I've never experienced that implementation of an ETL is the bottleneck. It's always understanding the source data and understanding the like data quality rules that you want to impose to convert the data. It's understanding the content, not implementing your understanding.
Feels like a terrible question to ask in this building, but like I can see just from my own group, you know, let's say there's a skills gap, like, you know, you understand the data, you understand the ETL, you're used to like BI work, like counting things, but then like the statistical knowledge around, let's say the methods, like, you know, is there a particular sort of training, you know, to kind of fill that gap a little bit? Or, I mean, does everyone have to learn statistics or how is that approached?
No, it's a great question. And I'll go back to this idea that we need people to do we need individuals to do all the different pieces, because it's not a reasonable thing that one person needs to know everything. But within Odyssey, actually Nicole's led several of these, we have lots of tutorials on the statistical elements, like how do you do this? Your last was how to do a network study, and like walking through the steps, both the social political parts, as well as the technical parts, as well as the statistical parts.
Yeah.
We give training on causal inference, on machine learning, on characterization. So those trainings are all available on the Odyssey website. What I generally say though is like make a team of people who collectively have the skill set. Don't try to take it on yourself. Not because I don't want people to learn, but because it's overwhelming if you try to do it all. Like it's just too much. And you know, what I've appreciated about our community is like, there's always somebody better than me at every item. So my goal is to get like, you know, I want to be the dumbest person in the room by getting smarter people doing all the pieces. And when that has happened, like consistently 100 times out of 100, like good things happen when you get the right team aligned on an objective.
Got a question online in the chat from Jacob Vu, noting that health is a very broad concept, starting from there.
Jacob, can you say more about what you mean by workforce and other domains?
Hey, yes, I can.
He's doing a project at the moment with ACT Health and ANU, looking at the health workforce more broadly, as in what, basically trying to predict, because ACT is a complicated place, what workforce we'll need over the course of time based
like
on
number of nurses, number of doctors, that kind of thing, or number of facilities.
Not quite sure where he's going though. What questions are health and workforce domains? Oh, maybe he might be just thinking more broadly. Jacob, I don't know if you're still on there.
Are you on, Jacob?
About beyond the health system, maybe that's where he's going.
Yes.
Oh, there you are. Go ahead, Jacob.
Jacob, you do it.
Yes. More like I noticed that the current common data model, there's a lot around services data and things like that. But you do have one segment that's on standardized health data that looks at location, the case site, and provided those tables. And I just wonder, where does workforce data more, I guess, you know, generally speaking, like number of nurses or allied health professionals, those kind of stuff fit into the model, or if there are any plans to incorporate this in future model. So yeah.
Got it. That makes sense. Thank you, Jacob, for the question. So yes, I didn't mention it when I went through the common data model, but there's an entire section on health data infrastructure, which is things like provider and care site. And we do some analyses in that space in the community at large. Specifically, your question about like number of nurses for a certain, like number of nurses, we don't have something that explicitly models that. Like it's a seems like a very valid and useful use case, but that hasn't come up actually in any community conversations that I'm aware of. I will say more broadly, there's the OMOP common data model, like the core set of tables that everybody has. And then there's an array of different extensions that organizations have created to facilitate their own specific needs. So for example, there's an imaging work group that has created an extension to handle DICOM data. There's a work group that's created geographic information system information to capture location information. So like if there was some workforce component, there could be an opportunity like create a work group and create an extension, and that would be something that could grow out of the work. I have not heard that use case come up, but it's an interesting one. I don't know why it hasn't come up. But it's an interesting one.
I suspect part of what Jacob's going to is also the conversation that we had earlier about, Patrick, about the sort of national data collections here in Australia, where we have the IHACPA submission, which is really just our hospital activity data, which is very high level, but we then have the National Hospitals Cost Data Collection, which is not a compulsory submission for jurisdictions, but that drives the national standardisation of a cost of an activity in an Australian hospital. And that, from memory, and someone here might know more about it than I do because I'm not no expert, tries to capture when a old man like me walks into a hospital with a fractured patella, the average cost of that is X. And from memory, it does factor in both the services delivered and the staff present. But as I said, someone here might know far more about this than I do. So it's probably in our national collections data, in the activity data sets, and maybe in the cost data sets. But I can see where Jacob's going, like in Australia, because these activity submissions drive the funding to our jurisdictions funding the health system. Then it would be something of great interest to Australia, I'd imagine, to capture what staff are present and what flavour of clinician they are.
That makes good sense.
But if it's not part of the core model, that makes absolute sense. Okay, I get that.
Yeah, I mean, like what I have seen in the community, particularly like in the health economic spaces, what people will do is they'll perform analysis to count up things like hospitalizations and length of stay, and then they'll multiply that by some factor.
Yep.
But I haven't seen people say like, this encounter used this number of nurses. I haven't seen somebody have that data, but if it existed, I don't see why it would be a problem to create an extension to accommodate it.
So I guess the closing statement, shut up, is that the core data model is the core data model, but there are various plugins to that for people who have interests outside that core model. Yeah, they can be developed and refined, and they all meet the same criteria of using standard criteria, controlled vocabularies.
That's right. That's right. And the extensions, because they're extensions, we don't have an expectation that all partners use them. So you end up creating sub-networks of those that have the extension that you want for your network studies. And that's totally fine.
Gotcha. So these, sorry, go.
No, there you're good.
I've got a million questions, so I'm going to stop. I need to stop.
Do these extensions?
There you go.
Do the extensions follow standard schemas?
Yeah, so in general, we have an idea of how we name tables and fields and data types, how we accommodate the vocabulary with concept IDs and that kind of thing. So we try to follow principles for these extensions. And then usually what happens is someone develops an extension, they bring it to the common data model work group, and they will look at it and say, yeah, that seems to follow the conventions. We're not going to pull it into the core model, but like, if you guys get some data partners to work with that seems like a good thing. And we've got, multiple examples of that playing out in the community right now. One more, last question.
Hopefully this is a good way to end, because I wanted to kind of come back to your thing that you started with about exhorting people to adopt a path towards stewardship of the collected data under the model. But also what Sally said about lifting the game, and about Australia being actually our hospital system being so we try to keep people away and out, and people come into health data from very many different places. So are there any examples or communities that you might be able to speak to with a similar kind of heterogeneous bunch of like people involved at the many different steps of OMOP or ETL that you could inspire us with? I suppose as an alternative to, say, the Korean model, which is so great, but that's because they're set up for it because the quality of their national data is so good already anyway.
Yeah, so I definitely think you can look at other parts of the world for inspiration to think like you're not alone here in Australia. I'll give a couple very brief examples. In Canada, there are different provinces every province has its own healthcare system. They do reimbursement through claim systems in the provinces, and also they separately have EHRs in the provinces. If they want to do anything at a national level, they basically have to have a network of their provinces. They are currently in the process of adopting the OMOP Common Data Model, and not too dissimilar from saying like there may be certain states here in Australia that are going to be easier than others. Same thing happens in Canada. There are certain provinces that are easier than others, but they are working towards that path. In the US, there are networks of hospitals that are adopting the OMOP Common Data Model where they like try to centralize the data. So the US Department of Veterans Affairs, for example, has 170 different hospitals across the US, but they have created something called Vinci, which basically is one common data model that has all the data from all the different hospitals brought together. And what that's enabled is like different researchers who used to have to work in their one local data silo now are able to work together. And the VA colleagues have presented that. In Europe, there's several countries, but I'll highlight specifically in Finland. They have national data, like national registry data, and hospital data in different academic centers. And what they've found is there's different maturity in terms of like national data, national registry data is like really robust and nice, but usually you want the depth of the clinical data. And so they've created something they call FinOMOP, which is basically pulling all those pieces together. And so everybody's at different maturity levels, but what the one common theme you see is like bringing these people that were basically doing all this research separately, by bringing them together into like one community, they're actually getting a huge accelerant on what they're able to accomplish. We're seeing that play out all around the world for sure. All right, Nicole just gave me a next slit. So I think I'm done. I will see many of you tomorrow at, are we?
9.
At 9 a.m.
Please arrive 15 minutes early, at least.
Be here at 8:45 for those who want to go through or fun with ETLs tomorrow. And thanks for everybody for your attention. I appreciate it. Thank you for listening online.